Okay, in the first couple examples I did with equilibrium, I showed situations where we didn't have any products. That made it clear that the reaction was going to have to shift towards the products so that there would be some of them in the equilibrium. But in some situations, we might have both reactants and products before or in the initial situation at the beginning. And so we don't know if we're going to make more reactants or we're going to make more products. So we have to do a calculation to figure out which way the equilibrium is going to shift before we can solve the problem. Here's an example of that. Consider the equilibrium. Iodine gas and chlorine gas are going to react to form iodine chloride, and that's going to be a gas as well. And we're going to assume that we have 0.2 molar of each, and the equilibrium constant is 2.4. So we're going to figure out first which way the equilibrium is going to go, and second, then we will figure out what the concentrations are at equilibrium. To figure out which way the equilibrium is going to go, we're going to use the reaction quotient. So here we're going to have the concentration of the reactants, iodine chloride over iodine. That's an I don't know what I'm thinking. There we go. And chlorine. And we include everybody because they're all gases and their exponents, their coefficients. And each of those is 0.2 molar in the initial situation. So this worked out pretty straightforward. My Q at current conditions worked out to be 1. So Q is less than my K value, which I set at 2.4. So what that means, if I remember that I'm dealing with products over reactants, since I'm too low, I'm going to need less reactants and more products, or this is going to favor the forward reaction. With that in hand, I can set up my ice chart. Iodine gas and chlorine gas are going to form iodine chloride. I have my initial, I said they're all 0.2 molar. My change, my equilibrium. Since the forward reaction is favored, this is going to decrease, and this is going to decrease, and this is going to increase. Just for the sake of argument, had Q been greater than K, then the reactant X's would have been plus X, and the product X's would have been minus X, as in it would have gone backwards. Since we're going forwards, we have our usual minus X, and 2X. So then I can get expressions for the concentration of each product at equilibrium. And I'm going to end up with a slightly annoying thing to solve. So K is going to be equal to concentration of iodine chloride squared, because the coefficient, over iodine over chloride. So what do I get? 2.4? 0.2 plus 2x squared, 0.2 minus x, and 0.2 minus x. Now maybe, especially if you watched the previous video, you're thinking, ooh, this is nice. This is one of those situations where I could square root both sides and solve this easily. And I could, but just for the sake of it, I'm going to go the long way here and multiply out these quadratics and see that that works as well. 2.4 equals 0.04 plus 0.2 times 2 would be 0.4 times 2 is 0.8x plus 4x squared. And that's all going to be over 0.04 minus 0.2 times 1 times 2, so 0.4x plus x squared. Now I'm going to bring all this up and multiply it by the 2.4. Now I'm going to move everybody to the, it doesn't really matter, I'll move everybody to the left-hand side, or the right-hand side, so I'm going to get 4x squared minus x squared, so 3x squared, 0.8x minus, plus 0.96x, so 0.8 plus 0.96, 1.7x, 1.76x, and then 0.04, hold on, 0.04 times 2.4, yeah, okay, no, that's right, 0.04 minus 0.096, getting me negative 0.05x. That's a decimal place. Okay, so I can use the quadratic equation to solve this. X is equal to negative b plus or minus the square root of b squared minus 4ac divided by 2a minus 1.76. Since this is a minus and the bottom here is going to be a plus, I'm going to need the positive root to make sure I get a positive value for x. So I'm only going to solve for that one. That's going to be the root that turns out to be the right one. B squared is 1.76 minus 4 times 3 times negative 0.056 all over 2 times 3. So, punching through all of this, I end up with 0.03 for my x value. You can use a quadratic equation. If you look online, depending on your calculator, a lot of calculators will solve this if you just input the quadratic itself. It'll give you both roots. Because we were careful with our q, we need to make sure we're using our positive x root here. So this is the x value, 0.03. I'm going to go back now to here and say I could have just square rooted both sides, and I would have ended up with 0.2 plus 2x over 0.2 minus x is equal to the square root of 2.4, 1.55, and then 1.55 times 0.2, 0.31 minus 1.55x is equal to 0.2 plus 2x. Moving my 1.55x over here, 3.55x, and 3.31 minus 0.2 is 0.11, and 0.11 divided by 3.55 gives me x is equal to 0.3, which is what I got, or 0.03, which is what I got by doing it the big, long, hard way. So if you spot this perfect square, then it's going to save you a lot of trouble. If you don't, you can always hammer it through the old-fashioned quadratic way. Either way, we get our change x, and we can come up with our concentrations at equilibrium. For our iodine gas and our chlorine gas, they're the same at 0.2 minus 0.03, or minus x, which gets me 0.17. And for my iodine chloride, I created two x's, which gets me 2 times 0.03, or a concentration of 0.06 molarity. So, if you have reactants and products in your initial situation, you need to find the reaction quotient to figure out if the forward reaction or the reverse reaction is favored. Once you figure out who is favored, you can put the x's in with the appropriate signs, come up with your expressions for your concentrations at equilibrium, solve for them in the equation. If you're smart and you recognize perfect square or something like that, maybe there's a shortcut, maybe there's not, and you have to use all your math from grade 10. Either way, you can then substitute back into your original expressions and come up with the actual concentration of your products and reactants at equilibrium.